latest release, you'll find binaries for OS X or Windows or whatever. So you can download it there and run it via that.
You have to speak up, Zubin.
Okay. So to run Z3 as in the interactive mode, you give it the -in argument, and it drops you in an interactive mode. So what Z3 is it's a language for it. It's a solver for constraints. So the language it accepts is called SMT-lib2, which looks a bit like Lisp if you're familiar with that. So the way it works is you declare variables like this. So I've declared a Boolean variable, and then I can assert facts about it. I can assert not X, and I can assert a bunch of facts relating a bunch of variables that I've defined, and in the end I can do a check sat to check if these facts are satisfiable. So Z3 responded by saying that these facts are in fact satisfiable. So what this means is that it can find an assignment to this single variable X such that not X is true. So the assignment is pretty simple, it's just false. So to look at what actual assignment G3 deduced for this.
So you do get model.
Get model, yeah. So we see that X is defined as a function from nothing to bool. So declare const is basically sugar for, or basically a short form for a nullary function. So all symbols in Z3 are in fact functions. So symbols that aren't functions are just nullary functions. So these are mathematical functions, not like pure functions, not like functions in a programming language. But
it's a constant. Yeah,
it's a constant. Yeah. So X is a Boolean and C3 has
because it supports, like Zubin said, SMT is quantifier free. Okay, so a constant is an uninterpreted constant. Okay, so it can be a function. It's really a function. It can be a zero-ary function. So an uninterpreted constant can serve like a variable. So that's the concept.
So we can also declare relationships between variables. You can say, for instance, implies x1, x2. I declare two new constants, and this means that x1 should imply x2. So we can check sat for this, and it's satisfiable. And if we look for a model, C3 will tell us. Sorry, keep messing this up. Good. It says one particular model of this is X is from before. We can ignore that for now, but a model is simply false and false. But what if we wanted to get a different model for this? So we can assert, assert that x1 is true, which means that this model will no longer be valid because this model assigns x1 to the value false. So if you assert x1 and then check sat again, we know that is satisfiable, but now the model that Z3 has assigned was the same form was changed. So both x1 and x2 are true because we previously asserted that x1 implies x2. So the syntax for this language is prefix style. If any of you are familiar with Lisp, it's basically a Lisp with S expressions. But Z3 supports other data types also, but we'll not really be looking at them today. So you can have things like integers, and the way you would express relations between integers is you would use prefix syntax. So if you want to say that I is greater than 10, we would write it in this way. So then we can check that and get model, and C3 assigns I the value 11 and so on. So the constraint language is pretty rich, and what our primary goal is to use it to model transition relations. So in the last class, Professor
Oh,
Srivas discussed.
just a comment here. Yeah, we will be, since at least in this model checking course, since our focus area is finite state systems. So our universe is discrete and finite. So we'll primarily be using propositional logic. But sometimes we can veer into, because Z3 is more powerful than just being a solver for propositional logic. Sometimes we can explore into some bounded integers, bit vectors, and so on. Okay. Yeah. So that's a point that I just made. Yeah. So you could, you know, uh, veer outside of a propositional logic, which we are doing anyway with quantifiers, the quantified Boolean formulas. But even in the domain, if you wish, you can do with bounded integers if you want to use that.
Okay, so this transition relation was discussed in class. Uh, Two states x1, x0. The states are represented by pairs of booleans. So the first state is x1, x0, and the second state is y1, y0. And y1, y0 is a successor of x1, x0 if y0 equals x1 or not of y1. So this is the relation discussed in class. So now let's look at how we would model this relation in Z3. So this is the same relation copied out over here. So lines that begin with semicolons are comments, but yeah. So what we want to do is we want to define a function that accepts that a function which accepts 4 booleans and returns a boolean, which basically defines this T relation. So the
It's just like a macro. Okay.
yeah,
So don't, So T is just a macro. So you can maybe
so
find it out.
it takes
Yeah.
4 arguments x1, x0, y1, y0. They're all booleans, and it returns a boolean result. And the boolean expression it returns is the same as this transition. Y1 equals x1 or and not of y1. So let's see how we can use this to compute the image of our transition relation. So first we declare that we have 4 arbitrary Boolean variables x0, x1, y0, y1. We can assert this first property here that the satisfiable models of this particular formula, that x0 and uh, t of s1 and s2. So the way we do this is we simply just translate this into the SMT-lib syntax and assert it. So and of x0 and t of whatever, and uh, we can use Z3 to uh, check this file and give us a
One subtle point that I want to make here is Zubin ended up using the same thing. So the macro is defined with respect to some variables. He ended up using the same formula
so
as well as the constant. So he's actually instantiating each
so these can be
constant, with
A,
that.
B, C, D,
But
and
yes, so
this
that's
can be.
exactly what is happening. Okay.
But
So he
let's
overloaded
just stick with this for now.
Yeah. Okay. So you stick with that.
Yeah, so we've got one particular model for this, which is that x0 is true as we required it to be, but x1 is false, and both y0 and y1 are also false. So what if we want another model that satisfies this, or we want all the particular uh, images of this, which is these 4 that were mentioned in the PDF. So what we have to do for that is we need to introduce a contradiction with this model so that this model will not be satisfied. So
Yeah.
we
So you
can
block
simply,
that model by
so we can encode this model and say, so this model is x0 true, x1, y1, and y0 false. We can just simply assert not of this telling the SMT solver that we want a different model. If you do this and check SAT, uh, so,
Right.
it's,
Yeah, no, it's okay.
no, it's the same model. Oh, I didn't get model. Okay, it's satisfiable, but if you ask it to print out the model it got, we can see it's a different model where x1 is true. So and y0 is also true. We can ask the solver to see if there are any other models again negating this model. So this model I copied out over here, x not true, x1 true, y1 false, y0 true, and I'm simply negating it, and we can check for satisfiability, and we get that it's unsatisfiable. So these two models are the only models it found. So these are the only satisfying instances of this formula. Uh, so at this point, if we do a get model, Z3 will give us an error because the formula is unsatisfiable. So there is no point. So we can, uh, yeah,
You show the QBF form, and
yeah.
then maybe you can ask them to do the two-step thing, okay, as an interactive exercise.
So
You've already shown.
yeah,
That's okay.
but yeah. So now, what if we want? So Z3 supports existential. Z3 supports quantifiers also, so we can have demo it. So we have declare x constants, and we have another constant. No, suppose yeah. So we can say something like assert for all x, for all y, which is a boolean. We have uh,
In X and Y. That's it.
yeah, x and y, yeah. So,
No, because you haven't declared. No, that's okay. You haven't done it, so this should work. So what is the?
I think the parentheses.
Could be. You had one.
Oh, sorry. This is the syntax. So this actually, the for alls actually take a list.
Yeah.
So
This is there.
so you can actually quantify over multiple
Yeah, but you have to
variables
close.
at once.
You have
But
to close the. Correct.
yeah, yeah. So you can check satisfiability for this formula,
First, yeah, okay.
and this is unsatisfiable because there's no y such that this will always be true. Also, there's no x such that this will always be true. If instead sorry,
Yeah, because for all Y requires.
yeah, but if instead I change this to an or, we know that if we set x to true, if there is, this formula can be true for all y. So we can get model, and we see that the model says x2. So Z3 supports quantifiers as well. So we can, even if Z3 did not do this, we could simulate Boolean quantifiers by expanding it out. So if uh, something is true for all x, then it's true when x is true, and it's also true when x is false. And if something is true for some x, or there exists some x such that a formula is true, then it is true when uh, either when x is true or when x is false. So we can always replace a formula like for all x bool some formula that includes x with, we can rewrite this to uh, p x equals true and so p x equals false. And if you have a formula like exists x such that p of x, then you can rewrite this to uh, p when x is true or p when x is false. So this would, uh, uh, but what this saves us is a more compact
Yeah,
way
go ahead
of,
with the examples of it because they've
yeah.
seen this expansion. I've shown them this expansion.
So uh, so if you want to do a two-step transition relation,
So
uh,
you guys understand the point that Zubin was making, correct? That you can always eliminate the quantifiers. I mean, you guys have to yell. Somebody has to yell. Otherwise,
or someone typing in the chat,
huh?
no one's typing. So someone
Are they there? Are people there or? Okay. So they said yes. Okay, fine. Go ahead.
So we can model two steps transition relation using that
First show
exists.
the QBF version of the image, and then let them do the two-step. You first show the. You didn't show the. I mean, first show the.
Okay. So I'll comment all of this out because we don't want this messing with our true state. But yeah. So you can say that uh, to uh, ask if a particular state is reachable from a transition relation, we can say, do there exist x naught bool, y naught, x1 bool such that uh, t of x naught, x1, y naught, y1. So if we remove this, we don't actually need to remove it, but for clarity, this might just be better. This is basically asking if uh, there is some initial state uh, from which we can get to y naught and y1, or uh,
What is, yeah, it says what is the set of
yeah,
all what what is the set of all inputs whose
uh,
significant bit is you. Now you're getting the images of all possible
yeah. This is all possible image.
states.
Yeah. So uh, this will result in all possible images of T. But if we uh, to uh, and now we can yeah. So the way to do two steps using this is if we have arbitrary states x1, x0. If you have arbitrary states x and y, we can, if uh, y is reachable from x in two steps, if there is an intermediate state z such that we have yeah. So uh, y is reachable in two steps from states x0 and x1 if we have some z such that uh, x0 goes to x goes to z in one step and z goes to y in another step, and then you can generalize to this to n n steps basically. So this is how you can model transition relations in z. So uh, one exercise might be to figure out how to uh, write this particular relation without using t twice. If anyone, so I'll give you a couple of minutes to think about it, and if you have answers, please type it in the chat. So the goal is to only use t once, and a hint is that you can use nested quantifiers for alls or something, and somehow use that to.
Don't get into that example thing. I want them to do something now. So I was hoping to give them this. Okay, go ahead with that then. So then you'll have to let them do. Okay, so why don't you explain?
No, I'll give them a couple of minutes to think.
Okay.
Basically,
You
you want to.
understand the question. So you have to ask the question. What is the question that you have? You already shown
Yeah,
this.
so
But that
the question we have to. So the question is this: we have a formula to calculate
yeah, but that's let's get something.
to assert transition between x and y in two
Really,
steps.
that's a
So
hard
x,
thing. Okay, so instead of getting directly to that, let them do something simpler. Okay, so you've already shown them the two-step. I was hoping you will ask them to do the two-step thing. So let them change. If you okay, so here's my suggestion. Okay. I mean, unless you can ask them to do so. I think that will require nested quantifiers. So let's take that. That's a little bit more. That's harder. So for them to get acquainted with the notation. So what I'm suggesting is the following. Why don't you guys change the transition relation? So this transition relation is just shifting the whole thing to the right, okay? So you change the transition relation to one which shifts it to the right and it kind of wraps around, okay? So it takes the least significant bit and puts it back into the most significant bit. And then check some things, okay? So we'll give you 5 minutes, okay? And then he'll move to the next harder thing. So what I'm saying is change the definition of T to make it actually shift the input to the right by one position with the bit that gets out getting moved into the thing. Okay, you don't show them, let them do that as an exercise. Okay,
so I'll give an example of what you want. So we want this, right? We want you to encode this as a SMT formula or as a logical formula relation, right?
I don't know what you're saying. So I just want to change the transition relation to get it.
So you want the transition relation
Yeah,
to look
so
like this, right?
yes, correct, yes.
So if you can encode this as a logical formula.
Yeah. So which means, but they'll be doing with why1, why not? Okay, so they will
Yeah.
doing it with this if x1 x0 was the input, then it has to become that. Okay, so you need to change the definition of the transition relation. Okay, so can you guys do that? So we give you 5 minutes. Whoever gets it first will show. Okay, and then we'll get to show the thing. So you can then do the same thing, or you can do even do 2 steps. You see, if you get the definition correct, then the 2-step relation should get the input back. Correct? So just change the transition relation. In that case, a model of the 2-step image should get it back to the same thing. I mean, I've never tried nested quantifier with Z3. That's not, you're trying that, the second one? So,
No,
but you have to have the exists outside for all inside. What are you trying to do?
I'm trying to encode the property that you'll get back to the original state after 2 steps.
No, but that itself, you can get it by just the model. Why do you want to state it as a property? You know, once you define the assert, you check sat, and then you get the model, and it'll, you know, you get back, you know, that's the only model, no?
Yeah, you can do that, but there's also another way.
That's better. Let's not get too much into the nested quantifier. You can get too fancy too quickly. Go one step at a time.
The question is that we want a relation that.
Yeah, so Argdeep seems to have a solution. So why don't you? This won't work, Zubin.
No,
So
the
how will it
solution
know
is.
their solution? So I think.
No, wait. It might, because the order of arguments is different.
So how is he showing you in the chat window? Is showing, is it?
Yeah. Yeah, this will work because, yeah.
Okay, show his solution.
So here, your solution, Argadeep's solution is this. X1 pool, X0 pool. Yeah.
Yeah.
So this will work, but the names of the arguments are a bit misleading. Because
I didn't notice that.
So what we really want is something like, I'm just renaming the arguments so it's more clear. So yeah, so basically this is cycling the bits over. So x0 x1 will be related to x1 x0 will be related to x0 x1. So
And you don't need to change anything. You can just go down, make, you know, assert the 2-step thing.
this one.
And you should be able to check sat and get the model.
So
Correct.
we need to give it some, let's assert x not to make it
No, no,
reduced.
no. That's not even necessary because it has given this as one of the models. So it's yeah. So it gave you the model, Zubin. I mean, you guys understand? So then you can get and if you block this model, it will give another model. Huh?
Yeah.
Yeah. So
So
did you get?
this,
You guys understand?
Yeah, how would you, is there a way to print out all the models satisfying something?
But that's a good
no,
question. See, I
so
don't.
the way to do this is to repeatedly check sat get model and then assert not of the previous model you got until you get an unsatisfiable.
I see, so there's no non-interactive way of doing it.
No, so you can use a program if you use a API for a programming language.
Right.
This is easy to work out. So
Yeah,
just run a loop.
a complete answer for this, Diganta. Is it Diganta?
Yeah.
Yeah, whoever it is. Yeah. So see, this problem of giving all instances, all models that satisfy the thing is something called max sat problem. Okay.
Hmm.
So some solvers do have max sat as a feature supported. Now I don't think Z3 does. So one way, if you do it interactively, is you have to block each model incrementally. Okay. Or what you can do is you write a program. Okay, that does the thing and it enumerates one model after another. Okay. That requires for you to use Z3 using its API. Now, let's not get into that now, Zubin, because we will not have time. So we will get into that, okay? Because there will be some assignments where you will be using the API. So we will get to discussing that API and so on. So there is enough information, about that also. So, but we will get to that later on. But suffice it to say that if the solver supports the maxsat, it has the maxsat feature, then it does that. Otherwise, you will have to do it, by blocking one at a time, for which you can write an actual program and automate that process. Okay.
Okay.
Yeah. So okay, go to the next one.
No, we can move on to n queens.
Yeah, I think that will be good. Yes.
Yeah, so
Or do you want to give them the pigeonhole problem? And then
okay,
you have a solution for it.
I have a solution for it.
Okay, so let's give them. So flash the pigeonhole thing, and give them. It's 4 o'clock now, so give them at least to model maybe one of the constraints.
Okay, so uh,
No, but don't let
yeah,
no generation. Okay, so
yeah.
get the my slide. Okay, which describes the pigeonhole. Okay.
So the pigeonhole problem is that you have uh, n+1 pigeons in n holes, and you want to prove that each, at least one hole has more than one pigeon. So, so you have n into n+1 variables denoting whether a pigeon I is in a hole j. All those variables be ij, where I ranges from 1 to n+1 and j ranges from 1 to n. So,
Yeah. So for you to do, so suppose you assume that n is, say you have only one hole, okay, and two pigeons. Or is that, yeah, I mean, I think maybe they can just, or two holes and three pigeons for some small number. And then
yes.
write it out. Write out the two constraints. Write out the two constraints, and then for The idea is that first you have to state that every pigeon has to be in a unique hole, okay? And then you have to also model the second constraint that two different pigeons cannot be in the same hole. Together, they should be unsatisfiable, correct? So, and that's the crux of the problem. So this problem, when you do both the constraints together, it will be unsat. It can never be satisfied.
So in assembly, for usually when you're using assembly solvers, if you want to check if the constraint A implies B is valid, you would start by asserting A. Valid means it's true for all possible all possible models. So you would start by asserting A and then asserting not of B, and then checking for satisfiability. And if you get an unsat, that means your original implication is valid, because satisfiability is kind of like there exists. It's precisely, does there exist some model which satisfies these constraints? So if there is no such model, then we can conclude that A implies B. So we would expect this to be unsat if our implication is true.
How can we do it for arbitrary n?
Uh,
Can we have loops?
use not an SMT-lib, but you can use indexes and
No. See, let's no, for
okay.
let's. Can you prove it for an arbitrary n? No, using stat solvers, you won't
no,
be.
you can't.
I mean, you have to instantiate it. You can only model and code it in propositional logic for a particular n. But the encoding, the encoding can be parameterized with respect to any n. In the sense, you can write a program which generates for any particular n the set of constraints that it, a set of constraints that are needed. Okay, that, and he will show. Zubin will show for the 8 queens problem. I think you have parameters for any n, isn't it?
Yeah, I've done it for N queens and even pigeonhole. I've also.
Oh, you have done it with Jolo. So you can show it. Yeah. So I'm answering the question, whoever asked it, that if you meant, can I encode the problem for an arbitrary n within a SAT solver? The answer is no. Okay. Because in propositional logic, you can only have finitely many variables and so on, okay? And only finitely many finite size formulas. And therefore, the answer would be no. And, unless you allow for quantifiers, okay? And since propositional logic does not have quantifiers, and since QBO is, even with quantifiers, is only over a finite number of, domain is finite, you won't be able to do it, okay? So with SMT solvers, with quantifier free, even if you have numbers, you won't be able to, you may not be able to do it for any particular, and unless you have, with quantifiers, you'll be able to do it, okay? So that's why I'm asking you, if you can, before Zubin shows his solution, spend maybe, the next, couple of minutes to at least code one of the constraints and show it to us, and then he will show the full solution. So
do I code it for like not in SMTs? I mean, not in Z3.
You can just give a
Yeah.
logical formula.
Okay.
Type it. I know that it is kind of difficult to type it up yourself with just one session that you'll have to do at home. But if you're just for us to get the feeling that you can. I mean, I'm sure that if you spend time, yourself, you'll be able to do these problems. It's not that thing. So just to keep it interactive is what I'm trying to do, not as a test or anything. Okay, are you checking it?
No one has typed anything.
Someone did. Ganta is asking something.
Yeah.
So one would be, yeah.
For some particular, for some particular eye, so and overall eye.
Yeah, sometimes in these kinds of problems, it is you might be, if you can you use quantifiers to describe the constraints, and after that you can enumerate over the entire thing and generate for any particular thing. So it's always useful to either have them as yes, use a quantifier or enumerate thing, and then you can enumerate. Yeah.
So the first part is exactly what Diganta said. So we have, suppose we want, so I've commented out the part that does the second part.
Explain what Diganta has typed to the rest of the class.
Yeah, so I'll explain it. So we have 4 pigeons in 3 holes. So we have variables p I underscore j, where I is the number of the pigeon and j is the number of the hole. So this variable says pigeon 1, indicates whether pigeon 1 is in hole 1 and pigeon 1 is in hole 2 and so on. So to assert the first part of this, we would assert an OR over all the, for each particular pigeon, and OR over all the variables mentioned in that pigeon. So P11, P12, or P13. So pigeon 1 is in hole 1, or pigeon 1 is in hole 2, or pigeon 1 is in hole 3. And we assert this for each of the pigeons. So we have 4 pigeons, so we assert this 4 times.
I guess Sahel is trying something. So Pratik Chandra has his question. What do you mean by your comment? Written keeping in mind Z3 Python API?
So he's written the Python code.
Oh, as we speak, he wrote it. Huh?
Yeah.
Oh, okay.
Only added the 2 constraints, nothing else.
Okay. That's good. Yeah. So, but you wrote the Python API to generate the constraints in what format? The question is for Pratik Chandra.
Sir, I wrote the general one. I mean, I think I have to code it to.
No. But see, but then if you, what is the output of your program?
Oh, okay. Yeah.
I mean, you will be able to ship it to Z3 only if your
Yeah,
output is in this
yeah,
SMT lib2 format, right? Correct?
yeah.
So
Let's see the
Rish-
screen.
Rishikesh is asking if it should be exclusive or.
Sir, actually,
In this case, it doesn't really matter because we just need the constraint that each pigeon is in at least one. So the statement of the theorem is not really impacted by whether that's exactly one or multiple, but you can add an exclusive or constraint if you want.
Yeah. Because the other constraint says you can't have two in the same thing, correct?
Yeah.
Therefore, so that takes care of it, right?
Yeah. So the
We
second
will have to have one constraint for there are exactly some n number of pigeons, right? So that will probably take care of it.
So we only take as many variables as we have pigeons,
As the number of pigeons, no?
whatever, into the number of holes. So that is already taken care of by that because it's all booleans. There are no integers here. So.
Yeah.
So for 2, we actually need to code that the formula we want to give Z3 to prove is that no hole has no all holes have less than pigeons. So the negation of this.
Okay.
Yeah. So basically we. So the code I wrote to generate this is basically generates a list of n holes for n plus 1 pigeons, and for each pigeon in each hole it generates a variable pi underscore j. And the first part is what I've already shown you, that for each pigeon you assert that one of its holes is true, and the second part is
Which part you generates all the declare things?
the declares are generated over here.
Okay.
So we get all of these variables and we pass these variables to. It's a list of lists where each element of the outer list is a list of holes. So the outer list has size n plus 1, and each inner list has size n, where n is the number of holes. So each outer list denotes basically a pigeon. So we loop over all the pigeons and assert that all of the hole constraints for each pigeon. So we assert an OR of all the hole constraints. So yeah. So now if you look at it this way, so now the second part is we want to assert that for each hole, so this bit denotes the first hole, uh, this bit denotes the second hole, and this bit denotes the third hole. And for each of these holes we want to check that two of the variables in this hole, or at least two of the variables in this hole, are true or aren't true when we want to assert it. So we can do this by transposing a list of pigeons, and then for each variable in the whole, each pair of distinct variables in the whole, we assert an and between them to assert that both variables have to be true, and we take an OR over all the variables in this whole. So, so the second part basically becomes not of.
Yeah, I think
For the first, I'll make it smaller. Yeah. So this is for when you have 2 holes in 3 pigeons. So uh, for the first, so you say, so for the first hole, we have either pigeon 1 is in hole 1 or pigeon 2 is in hole 1, or so basically you loop through all the pigeons. This is I coded this in a very naive way, so each constraint comes twice, once with its arguments reversed, like P11 and P21 and P21 and P11 occur in the same thing. You can probably eliminate this if you code this properly. But, yeah, in the end, we check unsat and we receive an unsat from the solver. So we can do this for larger pigeons also, and generates a lot of formulas. And eventually, let's see if Z3 will be able to solve this. Uh, Z3 is taking a lot of time, but let's hope that it will eventually solve this.
Yeah, but this
Leave
is
it
a
running.
problem that gets out of hand.
It is a hard problem to solve.
It's a hard problem, complexity-wise, to solve. Okay, so I guess what you guys should do is, first write out the constraints in a kind of a parameterized form, even if you want to do it using some quantifiers ranging over the ranging over the index for the number of pigeons and hole. Okay, because the variable is xph, where p holes, and then get convinced yourself, okay, that you have constructed the constraints, and then you may want to write that to generate in your own way, okay, to do it. Okay, so yeah, so can we move on to showing the
Yeah,
8
N
queen?
queens.
But yeah, there you show the formula, the structure, the formula, first in this index form, and then show your thing so that they will have some time to stare at the.
So Z3 was not successful in the time I gave.
Yeah, I think so. I think even the state of the art in this case, 20 apparently is as big as it goes up to. Okay.
Yeah.
This, by the way, this particular, you can get solution to this thing by just typing it up on Google. It is also there in the decision procedure book that I can actually make it available for you as a reference text, okay? In case you want to. But the best way is, I mean, you just type on Google. I mean, you get a solution to the pigeonhole problem. But I encourage you to just try it, just so you will get warmed up, with using Z3 and so on.
Okay, so this is the N queens problem. I'm sure you would be familiar with it. So we have to arrange N queens on a chessboard such that none of them can kill each other, and the chessboard is of size N cross N. Queens can move in their own row, up and down their own row, up and left to right in their column, and along any of their diagonals. So the way we do this in SMT is pretty straightforward. We generate n square variables.
Yeah,
It's
do you want
one,
to
two.
show the complete solution or not in
Yeah.
indexed form?
So I've left out one diagonal, but it's mostly complete.
Then I sent you that stuff, no? So
Oh yeah.
so just flash it once so that they will understand what the thing is, and then they can probably use that to write their own program and check it on Z3, which is what I suggest that you guys do as an exercise. Okay.
So this is the formula for when you have queens, when you have variables x ranging from ij1 to n. So you say that for each variable in its column, you can't have, if a particular variable is set, Xij denotes a queen at position ij. So if Xij is set, then nothing else in its row and its column can be set. And also you assert that nothing else in its diagonal can be set. And we also want to, so if we just had the above section, there would be a trivial solution where you set everything to false because these are all implications. False implies anything. So uh, to make it a non-trivial solution, we have to assert the additional constraint that there is one queen on each row in each row. So this is done by this.
So why are we doing asserting that there is one queen on each row as opposed
At
to
least one queen.
yeah, but as opposed to saying that there are like exactly n queens in total.
So that is a good question, but exactly n queens. So to assert that exactly n out of n square variables or exactly n out of k variables is true is a slightly complex kind of formula.
Yeah, but this
Yeah.
implies that, no?
Hmm?
This
Okay.
implies the other one.
Yeah, this
Yeah, this
implies.
implies the
But
other one,
in
but
this case, it does. But in general, if you have n variables and you want exactly k of them to be true, the formula you need to write to assert that is pretty complex. So in this case, we can simplify it. But
yeah, so we
that
are
can be,
using some insight from the problem to just
yeah,
simplify it.
yeah. We're using an insight from the problem to simplify it in this case. But that's a good question for an exercise. Write a formula to ensure that exactly k out of n variables are true. So you can do this at home.
Yeah, by the way, I mean, I want to go back to this question that someone posed. Okay, if something can be done for an arbitrary n, okay, see, as long as in general, if there is only one, when you say you're encoding the problem in an n, I mean, a quantifier free fashion, which implicitly you're allowed one quantifier at the outermost. Okay, so when you're checking a quantifier free formula is satisfiable or not, what you're really doing is putting an existential quantification, or over all the variables. Similarly, if you can express your constraint as for all, okay, something, then you may be able to encode it, okay, as the negation. So sometimes if the depends on your constraints, but if you have to move the quantifiers inside, okay, sub formulas, etc., then you won't be able to solve it for parametric and even with numbers and so on. Anyway, it's a side comment. Okay, go ahead. Show your program, Zulu. Yeah.
Yeah. So
You can explain, for each of those constraints, part of your program generates.
yeah.
So you get an idea.
So uh, first we generate n square variables for each
How many of you know
I and j ranging
program in
from 1 to
Haskell
n.
here? So is Haskell, you're more adept with Haskell or Python?
So Python.
Python, okay.
So the bindings are pretty similar in any language. These bindings just generate SMT-lib formulas, so they're easily inspectable. So like I was showing you the generated formulas, you could just see it in the standard out of the program.
Oh, I see. So Haskell you're taking advantage of that, is it? So
Yeah.
findings that generate SMT lib. But
Yeah.
doesn't such a thing exist even for Python?
Yeah, I'm sure. I don't think they'll output the native bindings won't output SMT-lib, but they'll output some kind of a login. So, but the advantage here is you can directly copy this. These formulas are valid SMT-lib too. So Python would. I'm pretty sure Python has some kind of login, but I don't think it's SMT-lib exactly. So it outputs some. It can output these the constraints it's sending to Z3, but it won't be in this format. So what we do is we generate n square variables for each ij ranging from 1 to n. So we declare x underscore I underscore j of type Boolean, and then we add the row constraints. So this says that uh, if a variable v is set, then uh, none of the other variables in its row can be set. So x not equal to j. This list comprehension, you can read it as set builder notation. That's basically. So uh, x is drawn from this range, and we're taking all variables I comma x, where x is not j, and I is the index of the variable we already have. Similarly, we can do it for this is for columns, this is for rows. Oh, sorry, this is for rows, and so this is for columns, this is for rows, and uh, this constraint is for one diagonal. So we go from we look at all variables in the uh, of the form I plus d, j plus d, where d ranges from minus n to n, and I plus d is in the bounds of the board, and also j plus d is in the bounds of the board. And we also had to constrain that d is not 0, so we don't get the same variable again. So to add the second diagonal, we add another constraint just with the parity flipped on j. So we get the second diagonal of the thing. And if we build this and run it, so we can see that for one queen there is a trivial solution. For two queens there is no solution, so it's unsatisfiable. For three queens again it's unsatisfiable, and for four queens it finally finds a solution. If you place the queens like this on a board, you'll get a solution. So this
So
works
your
for
program even generated this pattern, is it?
yeah. So we can ask for. So I think this formula scales pretty well. Z3 can. I'm not sure. I did test it on a pretty big number. Let's see if it can do that in a reasonable amount of time. Guess it can't. I can do 20, I think. Yeah, 20 does easily. So, and finally, before that, we assert the final constraint that uh, for each row, at least one element of the row is true. So there's one queen on every row. So this is how you can use interface with SMT solvers with your programs and generate whatever kind of constraints you need to solve. Yeah, I think that's
So,
it
would you
for
mind
now.
scrolling down in the main function?
That's it. So the main parts of this is basically setting up the solver. This is taking some input. This is generating the board. This is generating a variable for each element of the board, and then we add the row and column and diagonal constraints for each of those variables. Finally, we assert that there's one queen on every row, and then we check if it's satisfiable, and then we get all the assignments that Z3 generated and use it to generate our board. Yeah, it's pretty simple, just around 50 lines. Any questions?
Is this are the Haskell bindings well documented? I was trying to look them up, and I
There
don't
are
know.
lots of them. I'm using something called simple SMT, which are very bare bones, but they work well enough. But there are lots of them because there are lots of different Haskell bindings to SMT. So
But I suspect there's but certainly there is a Python API
This is the official Z3 Python API, but
Yeah.
these bindings are independent of SMT solver. So these will work with any kind of SMT solver you have, the ISIS or Y3 or CVC4.
Sir, I have a small doubt actually.
Yeah.
Hello,
Yes,
Yeah.
yes.
sir.
Yeah, you introduce yourself.
Pigeon, I'm Kapil.
Kapil. Yeah, okay.
Sir, the pigeonhole principle, the statement is like A implies B, where A says that there are n pigeons, and B statement says that no two pigeons are in same hole.
No, B A implies if you're writing it as in
A,
form,
A
A
has
implies
n
B.
plus one pigeons, yeah, n plus one pigeons.
Yeah.
At least n plus one pigeons, and
Yeah.
B says that two of them are in the same hole.
As at
So
least one pigeon, not n plus one pigeon.
I said okay. And anyway, so so now, yeah, if we just put assert A implies B, this will return a set, right?
So if you want to do that, you'll have to do something like for all
Assert A first.
x naught, x1, and so on. All the variables you're using for p00.
What I'm saying is we can do something like this: assert A and then assert A implies B.
No, I think what he's asking is more fundamental question than any of these for all thing. So what is your question? I'm not quite sure that I understood your question.
Okay.
So
The statement A represents that there are n plus one pigeons,
correct.
and statement B represents that no two pigeons are in the same hole.
Yeah.
Now we want to check this in Z3. So we just put if implies AB, assert implies AB, then we will get set, right? Because A can be false and B can be false too. Just
Yeah.
assign everything to false.
Yeah.
Correct.
Okay, so to solve this problem, what we need to do is assert A first,
Yeah.
and then assert A implies B, right?
No, that won't work because in general you might have B. You might have B is no, sorry.
What is it that you want to prove? I mean, what is it that you want to check? A implies B is SAT, or what is it that you want to check?
Check if this is unsatisfiable or not.
If some formula is unsatisfiable.
So
Yeah.
if A is not satisfiable, in fact, then
Then
you'll
A
get an
is
unsat, right?
Satisfiable, right?
If A is not unsatisfiable, you'll still get an unsat, right? But A implies B is still sat if
Yeah, exactly. If
A is unsat.
suppose if you put all variables to false, then A will be satisfied. A will be unsatisfied, and B will be also unsatisfied. And A implies B will return true.
No, but you've already asserted A. So if you assert A,
Yeah, exactly. That's what I'm saying. We need to assert A first, right? This is a very small question actually.
no, but if you assert A, then you're discounting the case where A is unsatisfiable, right? So if A is unsatisfiable,
right?
you get an unsat.
We need that there are n plus one pigeons.
If you have something like this, implies AB, and you do a check set, and you get an unsat, then you have a possibility that simply A was unsatisfiable on its own. That is one possibility, right?
If A is unsatisfiable, then A implies B is satisfied.
I know, but if you assert these two things together,
Sorry,
you get an unsat for both of them.
Yeah, then if you do a check set even before the implication, then you will know.
Yeah, okay, if you do a check set here, then in general this is not true because if B so basically what this is doing is checking if there exists B such that this, right? So it's not checking that for what you need to do is to check for all B. So you're checking an existential when you actually need to be checking for all.
Yeah, no, I think, well, your question is a bit more basic than as it relates to this pigeonhole principle, I presume, isn't it, Kapil?
Yeah, I think I'm in trouble with modeling the question.
Correct, correct. So let's discuss this offline. So we're almost to the end. Maybe this is the right. I don't think you can finish the.
I have a quick question, if that's okay.
Yeah.
Yeah. So is there a way to, can we manipulate the outputs of checksat or get model from within Z3, or is that like?
I don't think so.
No. Let's. If you okay, that depends on what. See, there is something I called. Okay, so you can either interact with Z3 at the file level by generating, like he was doing, formulas in lib2. I mean SMT lib2 format. Okay.
So what you want to look at is this.
No, let me finish. Okay. So that's what we refer to as APIs. These APIs, these are like programming language, okay, APIs. So they actually give you, if you, these APIs are with internal structures of what Z3 does, okay? So, these APIs operate on the data structures that are used by Z3 to model literals, expressions, formulas, and so on, okay? Then, yes, what is pointing out, then you'll be able to extract, get some things out of the thing. For example, if there is some unsat, it can even tell you what set of clauses for unsat and so on. So the answer to your question is yes, okay, in that sense. In the sense that you will be able to access something more than what you can access right now, which is just either it is sat or unsat, or it gives the model. So you can access internal data structures. So you will be able to access more at the API level. Now, if your question is, can I access the entire part of the Z3 SAT solver state? No, I mean, you will have to go so deep into its code, then you will have to do. So the APIs, the programming language APIs provide you, allow you to access more information of the state of the proof that SAT provides.
Yeah, I think I was interested in writing what Zubin is trying right now, which is, can we get out the output?
I don't think so.
Yeah, I guess that would be really weird if you could use like store whether checksat as a boolean. That would be pretty weird. Pretty cool.
So you can't,
Another question I have was,
why do you need it? So you can call SAT
just to do fun things with like maybe if I can store checksat as a boolean and then reason about whether or not it's satisfiable and try to.
So if you want to do that, you'll have to interface with it using.
Right. Yeah. Got it. I guess one of the things was you were saying earlier that asserting implies AB would require for all quantification, but if you've declared constants above, then you wouldn't need that. Right?
Then it checks for an existential, right?
No.
Satisfiability is an existential.
Let's not confuse. I don't think this has anything to do with quantifiers. Okay, so the question that was posed was within.
This is a separate question. I got the answer for the first one.
Oh, the first one I need to understand, what Kapil's thing was, but that's separate. But what is your question?
Yeah, no, I'm saying my first question was just about the one that you clarified and Zubin also clarified. Separately, I was asking if earlier on when Zubin was talking about how if you do an implies AB, if you try to check for it directly, then you'll have to preface it with for all P00, P01, etc. And so I think
in that context, I don't even understand. So what is the goal here?
So the question was that, so if I've declared constants P00, P01, I thought that would turn into for all, but I guess Zubin is telling me that turns into there exists.
It is always there exists. Huh?
Right.
So if you want to do for all, you have to take the negation and check check it is unsatisfiable. Maybe that was what the confusion of Kapil's question was. So in that sense,
I think either you meant that if this returns unsat, then the theorem is true.
if it returns unsat,
And the theorem is true.
then the theorem is.
This is what you mean, right?
If you've asserted A and then asserted not B.
Correct. If you assert, no, the whole thing will be unsat in the sense some portion of it will be, some subset of it will be not satisfiable. Because when you're asserting a whole bunch of things, it's like conjunction of all those things. Okay. So if that whole thing is unsatisfiable, there will be some subset of those formulas which will be unsatisfiable. I mean, of course, the whole thing is unsatisfiable too. So which means that there does not exist a satisfying instance, which means you're right, that the negation of what you have done, what you have put in there is valid, okay? Whatever that you have asserted, take them all together as conjoin them. Take a negation of that, okay? That will be valid. Means for all the variables in there, the negation of what you have put in will be true, okay?
So for Kapil's question, so suppose you have two arbitrary constants x and y. You want to check if x implies y. So you can, if you do what you were saying, if you assert x first, then check for satisfiability, you get satisfiable. Then you assert that x implies y and check for satisfiability, you get satisfiable. So this is checking an existential constraint. So you want checking that x implies, so x implies y is not true.
Why? Okay, the confusion is, so when you do this,
what you actually wanted to check was this. This is what you actually wanted to check, but which is false. But if you do what you were saying, Kapil, then you get sat in both cases. So what you were saying does not really work.
Yeah, but if you really want to check, I will not recommend, doing all these things. So you directly, if you want to check what is for all x, using only sat, then you take the negation of the implication and then check if it is.
So can you please repeat how exactly we are modeling this problem in that general principle?
Okay, so, well, I think today it will be, we will not have enough time. Therefore, I think what we should do is you try to model it yourself. I mean, I suggest that everyone model it not directly in Z3, but rather as a formula in a propositional logic. Okay, I mean, whether you want to do it for a particular thing or in a parametric way, I don't care for any specific thing. Then we will discuss that. Okay. And I think the problem was that we did not have a very clear definition in logic, okay, and we are mixing up this series of asserts and what sat and unsat does with what the thing does. So let's revisit this, okay? This question. So I think your question is a combination of as it applies to.
No, sir, I actually have got how the problem is modeled. I am thinking of how we are going to check this in Z3. Okay, so one of my interpretations was there is statement 1, right? Each pigeon is in first statement is that each pigeon is in some hole, and second statement we take the negation, all holes are less than equal to 1 pigeon.
Yes.
Okay, then we check if A implies B. If
no, we check, we assert it.
No, we check.
No, we don't check it
in those states. Which you assert the both and you take the conjunction. Okay.
Assert 1, assert 2, where 2 is this one, not this one.
Yeah, which means you're checking
And
the
then
conjunction.
we
You're not
check
checking the implication.
SAT.
That is the thing. That is the confusing point, Zubin. So, I mean, he's confusing with implication. So when you do this, when you do one assert after another, what you're doing is checking the conjunction, those two things, whether that is satisfiable
So
or
we're
not.
checking for.
Yeah, I was trying to model this thing with implies. That's why I was getting confused.
Yeah. So then if you model it as implication,
Yeah.
why would, so the pigeonhole principle is such that it is stated that if every pigeon has to be in some hole, and no hole should contain more than one pigeon together, you cannot satisfy. That's how it is stated. That's why you do it as a conjunction. Okay.
Okay.
Now, I don't, if you want to model this as, of course, if you want to view it as an implication, when you have A and not B, I mean, I don't see why how you would express it as implications. If you want to express it as implication, then you will have to more naturally stated as conjunction of two things. And then,
Yeah, okay. I was thinking in implication way. That's why I was getting confused. Yeah, you can do it by conjunction. I got it.
I think.
okay.
Time for the class is over. I think
So Sahil asked a certain question about trying to get the output of the SAT or unsat comment within Z3, right?
Yeah.
So if we want to express that a certain formula is satisfiable, we can do it just by using like quantifiers or something like that. Like, as in,
No, if you. Okay.
so if we say if
can
there's a
use
formula
implication.
phi x, huh?
Oh yeah,
Yeah?
go ahead. Go ahead.
Yeah, so if you have a formula say phi x, and if you want to say that phi x is satisfiable,
Mhm.
then isn't saying there exists x phi x basically a formula, a quantified formula that is satisfiable only when phi x itself, like that is true only when phi x itself is satisfiable.
But that's what SAT solvers are doing. Okay, so they
Yeah,
are
so
only checking. One way of saying this, there is no quantifier. I keep saying no quantifiers, no quantifiers. Okay, don't get confused. For the simple case of the quantified Boolean formulas, just put it aside. So without any quantifiers, if you check satisfiability, then it is as though you're checking the validity of there exists an X. Okay.
yeah.
So,
Digant, I guess. Sorry, go ahead.
yeah, but SAT solvers, just give you answer for that, the satisfiability question. And it is a derived fact that since they are only doing their exists, if you want to get for all X, you will, you can do the negation and then check for unsatisfiability. Yeah? But I don't know if that answers your question. So you were saying something else. I mean, if you had the ability to prove a validity of the full first order predicate logic, then you can of course check the satisfiability by checking their exists. That's what you're stating, correct?
Yeah, Digant, I think I agree with you, but I guess I wanted whether I could manipulate the model or not. That would be, get model is really the useful part, not check SAT. You're right, check SAT would just be replaced with quantifier.
So when we do get model, we
Yeah.
get the first satisfy. If the
An arbitrary satisfiable model.
arbitrary.
Yeah.
So when we want to get the another one, we not this. We don't want to do this, and then we get another one, another
Yes.
arbitrary one.
Yeah, you
Yes.
block the first model by every model can be expressed as some variable being something and some variable being something and so on.
Yeah.
So therefore, you can always express that as a formula, and then you take the negation. So that is the
And
concept of blocking that model. Okay,
Got it.
correct. So then
And you can repeat this until you get an unsat, which means there are no more.
Yeah.
Yeah. Nice.
So, but is there a comment or a question?
So that was a question. That do we get an arbitrary, or how does it decide which one to give?
So that is, which model does it give first?
Yeah.
That, we will be getting into SAT solvers.
I
Okay.
was
It depends on how there are various heuristics that it uses.
But in general, it's arbitrary because it can depend on the order you declare your variables in, the order of your formulas.
It is more than that. Okay, regardless of what, how you declare the constants, etc. That is not, because it uses certain heuristics. Okay, regardless of whether it does not depend on the declare const order. Okay, so once you convert it into CNF, it kind of there are various heuristics. So it depends on
Z3. It does because you can push in pop context, so it needs to preserve earlier works. You can't just.
Let's not get way ahead of our thing, okay? But those things, yes, pushing and popping is a different one. But the basic thing is that there are various heuristics which SAT solver uses to pick the order in which it will decide on a particular variable. For example, if a particular variable occurs more frequently in several clauses, it picks that first, okay? And there are very complicated heuristics depending upon the occurrence of these variables. So, and based on that ordering, if it is satisfiable, it'll get the moment of as soon as it gets a satisfiable instance based on that ordering of variables that it decides on, it'll give that. Okay. Now that is those heuristics are based on some part on the syntactic structure of the formula, as well as certain things like how many times the variable appears in what clauses and so on and so forth. We will be getting into this a little bit, okay, but this is a very big subject matter, SAT solvers and how they are designed, and at the core level, there is very simple technique, okay? Algorithm that it uses. But that algorithm, it depends on the order in which you consider the variables to decide on. So that's what it will determine, yeah? But I want to get back to Diganta's. I know that we are running late. We might even be terminated. So Diganta, your question, I'm not sure if it got answered. So you were saying something like, can you repeat your question? So if there is some existential...
No, so what I was thinking was that if you want to argue or model something like, say, if you want to say, if some formula phi is satisfiable, then do something else.
Those things, you can do it, okay? Now, but that is not checking, validity or the thing of a particular formula. If you're saying, oh, if something is satisfiable, then you do check the unsatisfiable or something else and so on, you can do that, yes? But that you could do even, and there are lots of algorithms, model checking algorithms, which actually do that, where they call SAT solvers as a black box, as a subtask. And they do those kinds of things. In the sense, they call satisfiability as a one step in the whole algorithm, okay? So that is very useful and does that. So there you will be making repeated calls. All those algorithms that we will actually be getting into model checking, it will be making repeated calls to SAT solvers. And some of those calls will be checking the satisfiability. If it is satisfiable, then you do something else. Again, unsat or sat, okay? But they can be done by using SAT solvers completely as a black box, okay?
Right, and they can be also done in like one top level call. If we do something like there exists x as that phi x, and then use that as a formula in our antecedent or something.
Maybe you can do it, but you don't want to muck around and go inside as much as possible. Avoid going inside the SAT solvers, okay, to do that. So there, I would just do. I mean, you should have a very good reason as to why you want to go inside the hood of a SAT solver and do the kinds of things that I guess Sahil was intending in his implying in his question. But we will see a lot of model checking algorithms as we move along, symbolic model checking algorithms, which do exactly what you did, what you just now described, by calling SAT solvers several times to check satisfiability of pieces of your formulas and then doing something else. Yeah.
Yeah. Okay. I think my question was more like, if we want to avoid calling stat solvers multiple times, how do we re-express the formula, maybe using quantifiers in such a way that we don't have to avoid stat
Yeah,
solvers?
but I don't know how quantifiers are, maybe they'll be relevant, but then you're moving out into different logic altogether anyway.
Yeah. Okay. So
Yeah.
I mean,
Yeah.
I don't know if it's, I don't know if like with or without quantifiers, how would one like avoid that? Mm. So if we want to do something like check the satisfiability of phi, and if it is satisfiable, then check the satisfiability of some psi.
But why would you want to do that? You will see in some simple model checking algorithms. Okay. So
Yeah.
when you have to, you want to do temporal logic, then you will do several things. Okay. So you will get to know that as to why that thing is done. What I'm saying is that you can do that even without you introducing quantifiers. Okay.
I see. Okay.
That is the point. Okay. Otherwise, you will be going to a different thing. I mean, the only reason I introduced the QBF was only to see the power of quantifiers and the compactness. Okay, so you would want to do in general, without quantifiers. Okay, and if you're at the Boolean level, then it's a different thing. Okay, then maybe you can extend that to quantifiers. Yeah.
Okay, so there is a way of doing it without quantifiers by like calling the SAT solver in some specific way.
That's right. Yes, yeah. And that's what we'll exploit.
Yeah.
So we want to stick to propositional logic and then do the thing. Okay. Although it brought the QBF as a side thing, QBF solvers are still not anywhere near the engineering marvel that SAT solvers are. Okay.
I see.
Therefore, even if you can encode your problem very well and compactly in QBF, expanding it out and then doing with a SAT solver might be mostly okay. Yeah.
Okay, so I see.
Okay, I think we should stop here. I mean, you can continue the discussion if you want, but I think we are, for the general. Yeah.
Okay.
We record it today. Thank you. And I think he has worked out more stuff, and then maybe we could next time maybe show, if there is interest, we could show.
I've shared the code with everyone on the chat, so.
Yeah, that code. But have you also done the
Sudoku code is also there.
Sudoku code as well?
Yeah.
But I think you should, sharing the code is one thing, but I think along with that, you should share the formulas also, okay? So that, just diving into your code.
I'll upload those formulas.
Yeah, you please upload the formula in a certain thing. And I'll also, for those people that ask questions with quantifiers and so on, I have a quantifier version of encoding all the constraints for Sudoku, okay? And that might be more relevant for the people that are interested in FMT, okay? And I plan to share that in the SMT course, okay? So for those that are taking the SMT course as well, you see it there. Yeah. So that will kind of address maybe some questions, but although it is not completely related to what Diganta asked. Yeah.
Zubin, can you also add a couple of Haskell tutorials? Like I don't mind learning it, but I have never worked in Haskell. Yeah.
So you don't really need to know Haskell for this course. If you don't understand, I can write this stuff in Python also if you need.
No, I don't mind learning over the weekend. I mean, I can give it a try. So I mean, just for learning, I was.
This okay.
Yeah, my suggestion is that, so maybe what Zubin you can do is to publish also information about the Python interface. Okay.
Yeah.
Let's see, both at the level that you are doing, the file interface level, and the other features, as well as the API, okay, which they might be doing if I decide to give a programming project, okay. So the concern here is maybe the Haskell interface, if it is really far superior to the Python interface, then the person who asked this question might have a point. Okay. By the way, who asked that question?
So me, Pratik.
So,
No, Pratik. Pratik Chandra.
oh, Pratik. Okay. Yeah. So it boils down to that, Zubin. So if there is a compelling reason for someone not, to actually switch over from to Haskell, with instead of, although he is more comfortable with Python, then we have to give that person a good reason. Okay.
Yeah, I will. If you need any examples in Python, I can write them in Python, or I will switch to writing future
But
examples.
independently, if Pratik, you want to, get the thing, that's up to you. You can work out something between you and.
Yeah, yes. I mean, independently, I wanted to learn Haskell. I mean, that's why I asked.
Okay. Okay. Fine. Okay. Thank you. It was, great participation. Yeah. See you next week.